Okay, I'm going to do a TDM multiplexing problem example here. And in this problem, we have synchronous TDM with input rates. We have inputs A, B, C, D, and E. A has an input rate of 450 kilobits per second, and the other four have a rate of 600 kilobits per second. We're going to assume no framing bits and no empty time slots being used to accommodate the slower input signal. So one of them's slower than the other four, basically. And so the first part is to show a picture, and so I will show 5 inputs into a multiplexer, and then I'll show the output at R total. And these can be labeled A, B, C, D, and E, and their rates are 450, 600, 600, 600, 600. Okay? And what you have to do for this, what we're asked for is a frame design. What you have to do for this then is figure out how do we make a frame that holds the appropriate number of bits from all of the sources. And if you think about this, in the time that it takes 3 bits from source A, this is 3 times the bit period of source A, is going to be 4 times 4 bits from source B. Bit period for source B. And that's because their data rates are in a ratio of 3 to 4. So the bit rate for signal A, 4 times that, well, divided by the bit rate for signal B is 450 over 600, which is 3/4. Because 3 times 150 is 450, and 4 times 150 is 600. In any case, if we take 3 pieces of data from A, if we wait long enough that 3 bits from source A arrive, then we're going to have 4 bits from B, 4 bits from C, 4 bits from D, and 4 bits from E. And this can be our frame design then. My R-tote kind of got in the way there. And so we can see here that we've got 3, and then 4 times 4, 16, 19 bits. And yes, we are going to assume bitwise interleaving at some point, so we have 19 bits in our frame. So the 3 little A's represent 3 bits from source A, the 3 little B's represent 4 bits from source B, etc. Because we have no framing bits, our tote is equal to the sum of the input rates, and it's 450 plus 4 times 600. And this comes out to be 2400, 2850 kilobits per second. Our tote is also equal to 2.85 megabits per second. Okay? If we want to calculate the multiplex signal's frame size, assuming bitwise interleaving NF is 4 plus 4 plus 4 plus 4 plus 3, or 19 bits. And finally, the multiplexed signal's frame rate. If they all had the same rate coming in, then it would be the rate of one of the inputs divided by the number of bits per input in the frame. But we have 2 different rates, so we better check that when we go R1 over N1, that's equal to R2 over N, or let me call this RA over NA, RB over NB, where NA is now 3 bits, NB is equal to NC is equal to ND is equal to NE is 4 bits. And in fact, If I double check that these rates are equal, they are. 450 is the rate for source A, and the number of bits from source A is 3, and the rate of B is 600, and that's equal to the rate for C, D, and E also. And the number of bits for source B is 4, and both of these are equal to 150. So that checks out, and that is in fact the number of kiloframes per second, 150 kiloframes per second in our output. Okay, hope this helps and is understandable. These are kind of fun problems to do, and hope that helps.